So today we have Zhao Zhang. I'm very pleased to announce Zhao is today's speaker. Dr. Zhao Zhang, sorry. Zhao is an assistant professor at Rutgers, and he's a former ML group lead at TACC, the Texas Advanced Computing Center. Zhao's research lies at the intersection of high-performance computing and deep learning, and it spans systems, optimizations, and scientific applications. He co-leads the cyber infrastructure thrust of the NSF ICICLE AI Institute and is PI for two NSF software institutes, hpcGPT and Diamond. And today he'll be sharing his work on Diamond, a particularly timely topic given the recent momentum and excitement around NERSC 10 and the American Science Cloud and everything else. So thank you very much, Zhao. I think you can take it away.
Okay, thank you, Steve. Everybody can hear me, right?
Yes, great.
Okay, awesome. Okay, great. So I would like to start with a story using Promoter, I think back in 2022. So at that time, I started to look into, reproduce the AlphaFold 2 results, and I searched online, I see OpenFold is available. So we were trying to run OpenFold on Promoter, and we collect the data set, right? And we log into Promoter. And there are a bunch of things we need to do first, right? We need to download the software, install PyTorch, install the packages required by OpenFold, right? And we need to scale it out to many GPUs. And the OpenFold implementation was using Torch Lightning. So we have to use Torch Lightning and use the Slurm launcher to be able to run across many GPUs. And we have to deal with the 12-hour walk clock time at that time on Promoter. So we need to implement checkpointing, checkpoint resuming because the training itself takes about 128 GPUs for 7 days, right? And we also download the data from Amazon Web Service. It's about 1 terabyte of training data. And we also need to keep track of the code version and data version, right? So all of these tasks are not that friendly designed for novice HPC users. And soon after, we ran out of node hours on Promoter, so we need to move to another machine at TACC. It's the Lone Star 6. But that machine is a little bit weird because each node now has 3 GPUs. Even though we use Slurm, the software environment is quite different because the TACC uses its own customized Python build on TACC machines. Well, on Promoter you can use Anaconda, right? So things are quite different. So we have to go through this software installation, deployment process again to make it run on Lone Star 6. It's not a trivial process, but we managed to finish it in a few days. And then we got a Insight Award from DOE where we are awarded like 200,000 node hours on Polaris. But Polaris runs PBS, so things are different again. So we need to redo this process in one more time. So during this transition process, many things can go wrong, right? So originally, we can simply run this Slurm launcher as run Python, the openfold.py with the data path, right? All in this command line. But if you consider moving this command line to another machine, things have to be changed. For example, like machines use different launchers. So some places you can use Slurm, but on Polaris, you have to use the PBS, right? Using the MPI run launcher. And also for affinity, on Lone Star 6, you only have 3 GPUs, so that you can bind one process to a node, but launch 3 GPUs. But PyTorch Lightning is a little bit different. Yeah. And also the scheduler, the data path, right? And the second obstacle is in software installation. OpenFold uses Anaconda Mamba by default, but it's not a recommended practice on TACC machines. And also CUDA driver, even though both machines, all these 3 machines are with A100 GPUs, and the CUDA driver and the software manager can be different. And another obstacle is the data management, right? So we need to move this 1 terabyte of data back and forth, between different machines, and then we need to ensure the data consistency and, update the file path in the command line. And the first part is the scheduling policy. So maximum walk clock time on Promoter was 12 hours at that time, and the Lone Star 6 is 48. I can't remember what was that number on Polaris, but it can be 48 or 24. I can't use that. I can't remember exactly. Yeah. So these are the obstacles. And if we think about training a neural network across the GPU clusters, especially under the NSF setting, they have probably 9 clusters across the nation, and they vary from point to point. Okay, and our goal of this project is like, ideally, we would like to train any model with any data set on any machine. And so that's motivate our design of Diamond. So what Diamond is a web-based platform for neural network training and fine-tuning across GPU clusters, and is portable and it provides a portable and reproducible environments across heterogeneous systems, and it provides seamless environment configuration, job running, and monitoring. So some of the key features, those like in dark black, are the features that are functioning right now. So we have a container builder where users can customize a container image on the target machine, right? And we kind of use a JSON-net-based abstraction to hide the heterogeneity of the software hardware system of the supercomputer from the users, right? And we also have a component that can generate the launch script automatically from users' natural language input. So we are also designing other components like fault-tolerant task manager, integrated data management, and real-time GPU monitoring. I will talk about them later. Okay. So this is the core architecture of Diamond. So users interact with Diamond using a web front end. Okay, and this web front end has a Diamond core, and we use Globus authentication, Globus compute to authenticate users and also to manage jobs across supercomputers. And the Diamond core talks to 3 different components in Diamond backend to manage the container image, manage tasks, and also manage different supercomputers. Okay, and yeah. So the supercomputer manager abstracts the system-specific complexity for multi-HPC support. It has a declarative configurations. So each HPC system is defined using a lab sonnet file describing module names, Slurm directives, and paths. And we also do dynamic script rendering. So Diamond uses JSON-net to generate Slurm scripts tailored to each supercomputer at runtime. This is like to say, so different machines, they use different what's it called, container engine, right? So TACC machines use Aptainer, and on Promoter we have Shifter. So with this configuration, we can expose the same container engine as the container engine to users, but on different machines they will be mapped to different actual engines. Yeah. And that's what this command translation is about. So we convert high-level user actions like run tasks on container into valid system-specific instructions. Okay, and Diamond also provides seamless portability. So users interact with a unified interface while Diamond handles the system difference behind the scenes. And given the size of a promoter, I don't think it's a big issue for DOE users, but for NSF users, because they have so many different so many GPU clusters, provide a uniform user experience is important over there. Yeah. Okay, and this is one of these examples showing the concept where we have, Conda install on Promoter. So through this supercomputer configuration file, it actually maps to the Conda environment that is available on Promoter. And the actual command that it runs is a module load mini forge the Conda install another package. And on Delta machine at NCSA, the command is also container exec, but through this configuration mapping, it will be mapped to aptainer exec -nv to enable GPU. So this is one concrete example. Okay, and this is the Diamond dashboard. If you log in, you can actually log in with your Berkeley Lab credential because it uses Globus authentication service. So you see this page when you land on Diamond, it will show you a statistics of jobs and the points. And the points are global endpoints that maps, each endpoint maps to a supercomputer, and also the data sets and the images that you have. And it also tracks your recent activities and some quick actions. Okay, so once you log in here, usually the first step is to build a container image, on the target machine. So if you look at the left-hand side figure, you can select a endpoint that is available. This starting procedure, to start this endpoint, it requires, SSH into the supercomputer, then start a global endpoint. So that's the only ugly part. Oh, that's one of the two ugly parts of Diamond. Okay, so you still need this manual procedure to start endpoint to make it available, make it visible in Diamond. So now you can select a endpoint, select the partition, which is the queue, and specify your account. And if you have reservation, you can do that. And then in the next step, you can specify the container name with the customized build location and the base image. So this base image is a Docker container image that's hosted on the Docker catalog. So you can use like NVIDIA container image, or you can upload your own Docker image for use. And with AppTainer, it allows you to customize the AppTainer container image. You can install other software and set up like environment variables. But all of these are without root access. So if anything that you need root access to modify the container image, you will need to build a Docker image. Yeah. And I know on Promoter with Shifter, users cannot modify the container image, so it's a little bit, the implementation is a little bit different on Promoter. Yeah, and after everything is configured, you can launch the start build command. It will build this image on the target machine. Okay, and after the building is successful, you will be able to see the image that is available under the images tab. Okay, and now we have the image. So the next job is to run the training job. Okay, so if you create a new task, give it a name, select select the endpoint, which is the supercomputer that you want to run on, and specify a partition, which is the queue. Then fill in the account name. I mean, all this information are automatically pulled from the machine, so you can select from a drop-down menu, and use the container that you just built. Okay, and here comes the second ugly part of Diamond. It's like you have to copy paste the command line they want to run under here, under this dialog box. Okay, then you can submit a task. And once the job is running, you'll be able to monitor the standard output and the standard error from Diamond. And here I prepared a pre-recorded demo. We customized the current Diamond service to adapt to Promoter, and we're going to show an OpenFold training demo. So here you log in Diamond, you log in through Globus. This is where it landed on. So this action shows, the Diamond is pulling out the information from all the endpoints that are available. And when data is imported, it will show a green light showing it's ready. So here you can see the NERSC endpoint, and we use this file path as the working directory. So all the images and the job will be run under this path. So now we go to images and build a OpenFold image. So here we select NERSC. This is a pre-built OpenFold image that is available on Docker. And because we don't customize it on Promoter, so we directly this is actually not a build. It's just downloading the image from Docker Hub to Promoter. And this is run on the login node. So if you wait, maybe I can forward a little bit. Yeah, the log file will be pulled and showed to users. If there is something going wrong, you can always go back to debug. But now we have the image ready, so we want to submit a task. So here we say we want to run this OpenFold training and select NERSC Promoter because and Promoter use QoS. So we have debug queue, constraint GPU, and specify the project, and we run it for 20 minutes. Yeah, then we copy paste the command line, which is that's ugly, I have to say. Yeah, then you submit task. So Now the task is submitted to promoter via Diamond, and you can see the job entries are there, but they're not created yet because the job is probably in the queue. So we just wait for the file to be created. I think it takes 30 seconds. Yeah, so now the job is running, and you can see in standard error, the global seed is set to this number. And if you check the standard output, now is set because each node has 4 GPUs, right? So we see this like DS accelerator to CUDA 4 times. So it's loading. Yeah. So now we see 4 GPUs, and I can move forward a little bit. Yeah. So here, so we are seeing this like training progress. Each of the logs actually printed out to standard output, and you can track how the training goes on just Diamond. Okay. And you can see more steps coming up. And also, if you check the standard error log, you'll be able to see some like warning messages showing the showing the actual configuration. We have 4 GPUs, and there's some warning from OpenFOAD saying the sequence was not found in one of the entry. Yeah, so that's the demo showing how to run OpenFOAD with Diamond on Promoter. Okay. So we also did a case study. So we have like six students with about half a year or 1 year training in HPC, and we asked 2 of them to deploy OpenFOAD on Frontera from scratch, which means they need to build a container image themselves. Okay, and for the 6 students, 5 of them cannot finish within 5 hours, and I have to hop in to look into their errors and help one of the students and resolve the bug, and he was able to run to launch OpenFOAD in about 4 hours. Okay, so that's without Diamond. But if they're using Diamond, the 2 students who start from scratch can finish in about 4 hours, and for the 4 students who use pre-built OpenFOAD image, they can start in roughly in 40 minutes, in average. Okay. So that's the case study. Yeah. So ideally, we would like Diamond to be, build the container image once, then run anywhere, but things are not that easy in the real world. So generally for the A100, the GPUs, images are portable. So the image that we build on Frontera, even though it's an RTX 5000 machine, the container image can run on Promoter and the Lone Star 6. But for those GH200 based machine, for Delta AI and Vista, because they use the ARM CPU, we need to use another, we need to build a container image that is compatible with the ARM CPU. And I think also for the Vera Rubin architecture in the coming NERSC supercomputer, that's the same thing. Yeah, we need to do some customized support to make it compatible with ARM CPU. Yeah, and Diamond not just works for deep learning training. I mean, the container building and the job launching logic works also for other HPC applications. Okay, so far we have tested Diamond on Frontera, on Lone Star 6, on Delta, and also on Promoter. And we're also working on Vista and Delta AI. These 2 are GH200 machines. And Polaris and Sophia, the Argonne, they use PBS. So we need to do some customization to enable, compatibility on the PBS machine. Okay, so particularly for Promoter, the adaptation we did is, we hard coded the queue names because Promoter uses QoS as queues, and the container engine that's available on Promoter is Shifter. So it doesn't actually customize container images, but instead it's directly download the container image and Docker image and directly use the Docker image. I think these are 2 customization we did for Promoter. Okay, and there are some ongoing development activities for Diamond. We're building this programming front end with Jupyter Notebook and VS Code so that users can start, for example, a VS Code a client in the browser and do coding on inside the container image on the supercomputer. Okay, it's a bit complicated. Yeah, but once they develop the PyTorch script, then they can start training using Diamond. And the second thing is like we are building this image management across cluster. Let's say you build one container image on a machine that you can transfer it between machines, right? And the third one is data management. So we are integrating the global transfer service and also trying to support Hugging Face dataset interface. So users can download dataset from global transfer or from Hugging Face, and they are also able to like move the data around between clusters using global transfer. And the first part is the GPU telemetry monitoring. So from time to time, with a lot of GPUs for training, we can encounter this straggler or GPU errors, right? So we want to provide this GPU monitoring with the neural network. For large language model training, we have this complex parallelism strategies like data parallelism pipeline, tensor, context parallelism, or even expert parallelism, right? So we are designing a visualization strategy to show the GPU in this complex topology and also, streaming their telemetry like memory usage, temperature, errors encountered, streaming those data to users to the web portal. So users can see what's going on and they can stop the training, recover from failure, or restart the training process through this web user interface. Yeah, so that's what we're working on right now. Yeah, okay, and that concludes my introduction to Diamond. But if you remember, I said the launch script has reflects many of these like heterogeneities in software and hardware systems of a supercomputer, right? So composing the launch script it's very time consuming in the beginning. So we also designed this Maple module as part of Diamond. So it's a multi-agent system that can automatically generate the launch script on GPU clusters. So yes, again, the challenges of composing these launch scripts because we need to deal with different GPUs. We have Intel GPUs, AMD GPUs, NVIDIA, right? And they have different drivers. They use different schedulers to learn PBS, right? And we also have different software management tools like Anaconda or native Python virtual environment. And these users use different deep learning frameworks. Some of them use PyTorch, some of them use DeepSpeed, and also Magtron Accelerate. They all have different launchers. And so that users must write launch scripts themselves for each cluster and match local settings, which is time consuming and really not necessary. So we designed this Maple system. It's a multi-agent system. So here, the input is users description of what he or she wants to run in human language. But it can also be a command line, a script that works already on some other machine, right? So we have 4 agents in this workflow. So inside this command synthesis module, we have extraction agent that extracts the key parameters from the human description of this command line, right? Then, very importantly, we have a script database. It's in the form of vector database. We have this script template database where this retrieval agent can select the most relevant templates from that database. If the user say, I want to run on Stampede 3 or I want to run on Aurora, we have a database of previously successful launch scripts. So the retrieval agent will be select the most relevant scripts and synthesize the command line, synthesize the launch script, and then the verification agent can test the script on the target machine. So if it's successful, the agent will return the output to user saying, hey, this is the command line you can run. And if it fails, then we have a debug agent which utilizes a large language model that we can do the web search on on GitHub issues or Stack Overflow, then use the LLM to refine the script, then to do the verification again. So if that fails, then we can then the debug will be in a iterative loop, so until it succeeds. But like if it fails 5 times, then we conclude that we cannot do that. So the user have to debug themselves. So eventually, we're expecting the whole system can produce a runnable, a correct and a runnable launch script for neural network training. Okay. So as I said, we have 4 agents, right? So the extraction agent that puts the key information, key parameters from user input. The retrieval agent that selects the most relevant templates from the database, and the verification agent that verify the correctness and the executability of the script, and the debug agent that revise the scripts based on the error feedback. Okay. So to evaluate, oh sorry, okay. As I said, the most important part of this design is the template repository, right? So we collect those templates across 9 machines, across 9 clusters. So they are like Lone Star 6, Stampede 3. Stampede 3 is the Intel machine, has some of the Intel GPUs. And also Vista, Promoter, Aurora, Delta, Delta AI, Bridges 2, and Amble. So we collect those templates. We have 35 verified templates collected from 9 GPU clusters, covering 4 parallel launch strategies, including PyTorch distributed data parallel, PyTorch FSDP, deep speed, and accelerate. Yeah, and this repository serves as a knowledge base that enables Maple to generate portable and executable launch scripts, under each different cluster. So to examine the effectiveness of Maple design, we did 3 sets of experiments. The first set tests Maple's ability to generate correct and portable launch scripts across the 9 heterogeneous clusters and the 4 parallel training paradigms. And the second experiment evaluates its debugging performance on multiple deep learning models and frameworks. And the third experiment, we compare the accuracy, efficiency, and the response time between Maple and these large models. So let's look at the first set of experiments. So the left-hand figure shows the comparison of Maple to other open large language models without retrieval. Okay, so Maple is with this template database, but all these open source models, they don't have this retrieval capability. So across the 9 machines and the 4 paradigms, we have 36 test cases in total. So Maple succeeds in 33 out of 36. But if you look at other open language models, Cloud has the highest accuracy with 22%. Okay, so then we figure out a way to ingest this retrieval, to enable retrieval for open models. If they don't support a vector database, through like add-on, we just like ingest all these templates as the context when we query the open language models. So you see with retrieval, then GPT-5, Amazon Nova, Cloud Sonnet 4, and Gemini, they deliver similar accuracy as Maple. Okay, so this is for script generation across clusters. And next, we did an experiment with 9 machines with 5 commonly used applications, including GPT-2, Vision Transformer, ResNet, and other 2 applications. So you see, when we generate scripts for just one pass, Maple can achieve like 73% accuracy, which is like 33 cases out of 45. And with 4 additional debugging loops, Maple was able to succeed in 43 cases. Yeah, and the failure rate was about 4.4. And the highest accuracy that from the open model is like Cloud Sonnet 4. So the accuracy is about 35.6%. Yeah, this is without retrieval. But again, if we enable retrieval for them, then GPT-5, Amazon Nova, Cloud Sonnet 4, and Gemini, they show similar performance to Maple, okay, with like 95% accuracy. Yeah. So if we compare Maple, so Maple only uses small models. If you look at this figure below, so we have 3 language models, 1 for retrieval, 1 for extraction, and 1 for debugging. And the aggregated size is less than 10 million parameters. But if you look at these large language models, the open language models and services, they are probably 10 times larger than Maple. Yeah. And also, we compare the round trip time, the latency for the query of Maple to other services. I mean, this is an unfair comparison because we run Maple inside the supercomputer that we're running, while all these services are called through the web, right? So that also means like you can use Maple within the supercomputer, so users don't have to worry about privacy or sensitive, information being released to these open language models. Uh, so it preserves the privacy, yeah, and also like low latency to enable interactive debugging for Maple. Yeah, so that's about the Maple. So we analyze those errors that we encounter for those large sorry for neural network training. So we see these errors fall into three categories. The first one is the environment related. For example, like this inconsistency in system configuration, drivers, or runtime environments across our clusters. And the second category is framework related, like this PyTorch, deep speed. So there are some incompatibilities or dependency conflicts with deep learning work frameworks and the communication backends. And the third category is user-related issues like configuration errors, missing resources, or improper software setups introduced during job preparation. So among these three categories, the framework and hardware-related issues, they are challenging to resolve. Like for most of the user issues, Maple is able to resolve them. But for framework and hardware, for example, we couldn't build like 0.3 on GH200 because the compiler mismatch on the ARM CPU and the zero implementation. And we also find out deploying PyTorch distributed data parallel on Intel CPUs is also challenging because both of these cases, they require the official framework updates and the implementation, to make it happen. Like simpler debugging from user side, couldn't resolve these issues. Yeah. And to conclude, Maple, again, is a multi-agent system that automatically generates, verifies, and refines launch script for distributed deep learning workloads, and it bridges gap between users' intent and system execution, reducing manual tuning and improving reproducibility across GPU clusters. And our experiments show that, Maple achieves over 95% accuracy, comparable to these 100 billion parameters models, while just using 10 billion parameters. And we have the preprint available over through this link. If you are interested, feel free. You can read it and feel free to ask me any questions. Yeah, and the Maple's position in Diamond is like once we have a command line, a launch script working on one of the clusters, then users don't have to worry about it when they move between clusters. This command line will be automatically translated into target machines to alleviate this burden for users. Yeah, and this is our team for Diamond. We have people from Chicago, from Wisconsin, and also NCSA and TACC. Yeah. Okay, so I think that's all for my presentation. I'm happy to take questions.
Thank you, Zhao. Yeah, we have plenty of time for questions. I have a bunch. There's at least one in the room. Maybe Roland, you want to start?
Yeah, thanks. How hard is it to keep up with all the different supercomputer upgrades, policy changes, and keeping track of, are they up or down, things like that? How much effort goes into keeping up with all that?
Yes. So in Diamond, once we log, okay, so upon the time that we log in Diamond, Diamond will pull this queue status from the target machine. So if the queue is down, it will be shown in Diamond. Okay, we can only submit jobs to the available queue, to the current running queue. But if during the execution the queue is closed, I don't think we can do that right now.
And if something happens, like there's a software upgrade and everything has to be rebuilt, or something like that.
We haven't been through an issue like this, but in practice, because we are running through containers, as long as the hardware is compatible with the container image, then it's not the issue. But if there is a disruptive change, then we need to rebuild the container image. Yes.
What,
so do you-
what if like slurm options change because there's?
I'm curious about like how much effort it takes to like just keep ahead of that, or if you don't keep ahead of it and you just debug when something happens, like a slurm option changes or the queue policies change, like you mentioned, runtime was 12 hours in the early days of Perlmutter, and then
Yeah.
it changed, or maybe a new queue option becomes available that might be worth taking advantage of.
Yes.
I'm thinking another interesting project might be if HPC centers could advertise their policies and capabilities and uptime and status in some machine consumable way.
Right.
Yeah.
I mean, there are multiple ways, right? So we can have a uniform, like metadata design for this information, and the HPC centers can publish their change, in a central place, right? Another way is like most of these centers, have this policy available in the user guide, right?
Yeah.
And we can use a large language model to interpret that, to use like some like tool farmer when they generate the command line, they leave that, they use a special token in the generative script, and they have to resolve this token by calling the external tool to figure out, the exact, for example, the maximum the maximum walk log time, right? So they can fill that out. But for now, it's a user option, right? So no matter what queue they use, they have to fill in the time duration themselves. So, the user still has to be aware of this policy change.
Okay, thanks.
I could ask, I mean, again, I have a bunch. I'll ask one and then we'll see if there are others online that have questions. Is Diamond, does it have any awareness of the user's allocations or quotas at the site?
Yes and no. So yes, in terms of it totally relies on the supercomputer to manage that. So here, for example, here, when the user submit the job, they have to specify the account name, which is a project. So if they don't project or they don't have a sufficient node hour available in this project, the system will report error, right? Will reject the job. So this error message will be forwarded to the user. So that means Diamond doesn't manage this like itself, but it relies on the system feedback.
Okay, but if a user's then thinking about which site to run at, they at least have to be aware of
Yes,
where they have enough time and stuff like that. Okay.
Right.
Anybody online? Yan, you have your hand up. Go ahead.
Hi, it was very interesting. And my question is kind of tangential. I know that the value of what you do is automation, having this agent, but at the intro, you mentioned that one of the limitations at NERSC is the limited runtime, and that you needed to do some hacking to do checkpointing. So
yeah,
did you solve this more automatically now with this new framework?
So generally for deep learning like applications, checkpointing is automatically enabled because those neural networks have to train for quite a long time. For example, the 175 billion model of GPT-3 was like trained on how many, like 16,000 GPUs for 2 months. So there will be performance degradation from networks, from GPUs, from GPU errors. So they checkpoint the model maybe for every 1,000 steps. And the program is able to resume from the latest checkpoint by default. And all same for OpenFold. So they already have this mechanism enabled. And most of these deep learning applications do. They implement this as a norm.
Thank you.
If folks online you could raise your hand or just probably even just unmute. I could ask another one for now. So you showed a little demo of a job running in Diamond, and that actually ran on Perlmutter, I guess, right?
Yes.
You didn't comment on like what happens to the outputs or the results of a run. Can you or maybe I missed it. Can you speak to that?
The output of the results?
Yeah, so I think you showed
the
like the
models?
standard out, but like what about like output files or like metric tracking?
Yeah, the models, right? Yeah, the model is still on the file system, so we don't manage the models yet. So the models are produced on the Perlmutter file system.
Is that something that like is of interest to kind of add in here? Because then it sounds like the user then probably has to like SSH into the system or you know, SCP to get something
Yeah.
out or something like that, right?
So what we're thinking about is to use Globus to move models around. It's same as image and same as data set, right? And we're actually thinking about to make a Diamond, you know, the next phase of Diamond will be to let users deploy agentic system automatically. So they train the model, they deploy the model as agentic system. So we can automate this process, you know, by connecting external tools and the LLMs they fine-tuned, you know. So we have to enable this, and we're thinking about using Globus to do this.
Okay, that makes
And
sense.
we need to have a registry, you know, user can register the trained model, right? And they can manage them across the machines.
Great, thanks. Other questions from any folks? I just keep going down my list.
So do you plan to make this, I saw you got this service, this, I mean, you can go to the Diamond website, but is that going to be supported? Like, I guess you're going to just provide this as a service, or you're looking for partners to kind of host it?
We can deploy it in two ways. One is to deploy, so we have Diamond as a central service, right, where users can log in to a central place, then run on many supercomputers, right? We can also deploy Diamond specific to a machine. Right? For example, like we can deploy a Diamond instance for Promoter. So users, when they log in, they only see Promoter, and everything is customized for Promoter, right? That's
And
also
is there a way around the first ugly step? I don't know if someone already that you mentioned that the SSH and Globus Compute Start, for example. Do you have
Right.
a there? I mean, principle you could use it. You know, you could use Super Facility API or something, but they still need to get a token.
Yes, because we have this two-factor authentication thing, right? Almost on all supercomputers. So one way to bypass that is Globus Compute has a multi-user endpoint. So Purdue Envo machine was the first machine to enable that. So it's like multiple users can submit to the same endpoint on Envo, and you do have to start that yourself. The user doesn't have to start it himself. Okay, so in that case, the user doesn't need to log in with SSH at all. So they can just leverage the multi-user endpoint.
Right. But presumably it doesn't let them bypass the MFA, right? But they just go and do that.
No. And it's still, the jobs are still mapped to the accounts available and deduct the node hours consumed that the user has. Yeah. I think it confirms all the policies with multi-factor authentication, but I may get involved like Globus Compute people to. I believe that's 100% true. It's just like I don't know how technically they implement that.
Yeah, well, I guess if you're doing the Globus auth anyway to get in, you must have done.
Right.
I mean, I just tried it now, and I guess I'd already logged into LVL because it let me straight in.
Oh, nice. You can use your Berkeley Lab
Yeah.
auth, right? Yeah.
So can you say anything about like what kind of hardware, software infrastructure you have to run the service? Is it a bunch of Kubernetes containers, or is it like a VM?
So I got most of the question. Can you say it again? So
to run the actual Diamond service, what kind of hardware, software stuff do you have? Like, is it containerized and you deploy it with Helm?
Oh, okay. So the Diamond service is currently hosted on a cloud service. I'm not sure if it's with a Docker image or as a standalone service, but it's on. I can't remember the name of the cloud service, but we paid. I think AWS. Is that AWS? Yeah, but we paid like a few $100, you know, for a year. So it's actually running on cloud service. And cloud, but it doesn't have any special hardware for Diamond because it's just a front end. There's nothing heavy running on it.
Just a VM or something running in the cloud, and
Yes,
Yeah,
yes,
okay.
yes, yeah.
Still got about 9 minutes. We do have a hard stop at 11, but that sounds like we should be fine. I had a couple questions regarding the Maple stuff you showed.
Sure.
You talked about accuracy. You ran some experiments and compared different models. Can you just say a little bit more about what's actually going on in those experiments, what you're actually testing, and what accuracy
Yes,
means?
yes. Okay, so the complete test suite has like 567 test cases that ranging from 9 machines, these nine machines, four parallel paradigms, and 5 applications. And those 5 applications are, I think they have BERT, we have GPT, we have Vision Transformer, ResNet families, but I don't remember the very last one. So it's a combination, but it's not exhaustive list. So my theory is, what matters for a correct launch script is the prefix that's released to the launcher, right? Other than that, it's just the regular Python calling of the script and the application specific parameters. But what matters is the preceding part, that with the launcher, the number of processes, the affinity options, and resource constraint, the queue name, right? So what we did for the first experiment is like we use the GPT family, we use the GPT models, we build a mini app. So we just make sure the scripts, the prepending part of the scripts is correct. And then we use a set of the mini apps to test its validity across different machines. So that's about the first experiment. It's the same mini app with different machines. And for the second experiment, like we use 5 applications on 9 machines, but just using the same framework. So that's why we have like 45 applications. And by success, it means the applications can run with the correct GPU process mapping and produce the correct training results. Not correct, but produce like training logs that we monitor, like showing that, okay, we have 16 processes, like we have each of them binding on a GPU across 4 nodes, and it's producing the training logs. So upon that, we call it a success.
Is it like some rule-based system to like verify, okay, it correctly ran 4 ranks per node?
Right.
Or something like this, or?
Yes.
Okay, interesting. And what does the UI look like for Maple, or is this still in development?
Oh, for now, it's just like a command line thing. So you type in you copy paste the command line from another machine, or copy paste the human description, and it's a command line stuff. Like we're going to build a web-based UI for that.
Okay, cool. And are you thinking about how Maple could like be extended to cover more of this kind of like definition of a workflow or orchestration of things? Just curious.
Yes. So I also have this hpcGPT project, right? Where I'm collaborating with NCSA, TACC, SDSC. So we're building this automatic user ticket replying system. And we analyze the tickets over these computer centers and identify 4 categories, like center policies, right? And there are some, we have 4 categories. The 2 challenging category are debugging errors and those machine status related tickets. For example, like my job was able to run yesterday, but now it crashes, right? Or my job has been sitting in the queue for 3 days. What's going on? Or my just like for these like real-time machine status tickets. So we found those 2 parts are the most difficult, and we're designing agentic solutions very similar to Maple to resolve this.
Yeah, we should chat more. We should chat more.
Yeah,
about
we can
that,
talk more. I can talk about ChatGPT, hpcGPT for another time.
Okay, yeah, great. Yeah, thanks for covering that. Okay, any other questions from folks in the room or online? Going once? Okay, great. Well, then I think we can probably end just a few minutes before the top of the hour, so we have time to switch over to our next thing. Zhao, thank you again so much for
you.
this nice seminar and all the great discussion.
Sure, yeah,
Very interesting work. We look forward to seeing what comes next.
sure, sure. Thank you very much.
Thank you.
Thanks, everybody. Have a good Friday.